Right. So vector projections can be useful. There are certain things we in 21C where we're doing vectors, they are very, very useful. I only found one particularly interesting application for somebody in the biosciences for vector projections from the book. I'm sure there's more. So I have one example that we'll do from the book. But the idea of a vector projection, let me give you my take on it. I know you saw in class, it boils down to a formula or two. I have the way I view it, and I'll give you my take on it and see if that helps with it. So the way to think of a vector projection is if I put two vectors that are not going in the same direction, vector A and vector B, and actually you do this quite often in physics, which some of you will be taking probably next year, I'm guessing. It is convenient in many cases to think about vector B as a vector that, the way we add vectors, you could think of vector B as the sum of two vectors, one of them being a vector that is going in the same direction as A, and another one going straight up like this. In other words, perpendicular to A. That was supposed to be an arrow. Okay, there we go. The one that's perpendicular right here, which doesn't get a whole lot of attention in this class, but that's called the orthogonal vector of B onto A. Orthogonal, remember, means perpendicular, so we just put ORTH. But this vector right here is called the projection vector, the projection of vector B onto vector A. And that's the one that we're supposed to know in 17B. So you can think of it as if you break down vector B as a sum of two vectors, one of them in the same direction as A and the other one perpendicular to A, that's what the projection vector is. It's the part of B that's going in the same direction as A. Okay. So the way I like to think about how to get this formula is what we first want is the magnitude of this projection vector. So what I want is, remember, magnitude is like the length. How would I find just the length of this projection vector? And remember, notation-wise, we would write this like this. We would write this as the length is the magnitude of the projection vector. Projection of B onto A is the length, or the magnitude. Now we have a special name for this. We're going to call this the magnitude of the projection vector, the component of B onto A. That's what that COMP means. But that's nothing more than just the length of the projection vector. We're just going to call it the component of A onto B, B onto A, sorry. Okay, so our first task is to find this. Let's try to find this length. So what I wrote here in green, you can call that the component of B onto A. Using plain old trig. I have this angle theta. I'm interested in the length of this side. I know the length of this side. That's just the magnitude of B. So which trig function relates this side and this side for this right triangle? Which trig function? From this angle here. Yeah, this would be the adjacent side over the hypotenuse. So that is going to be cosine. So the cosine of theta is equal to, we're going to call this length, remember, that's the component of B onto A, divided by the length of the hypotenuse, which is the magnitude of B. Yeah, no, it's okay. So let's solve for this. This is what I want to find a formula for, the component of B onto A. So the component of B onto A, if I just multiply this over, that's equal to the magnitude of B times, I'm multiplying that over, times the cosine of theta. Now you'll notice I left a big gap here, didn't I? I said this times this, but I left a big gap. And here's why. This is the way I think about it. I know Dr. Burke explained it a different way, but what does this right side almost look like? It almost looks like what formula that we just learned last time. The right side almost looks like the definition of the what have we been doing with vectors? What's recently? We have two vectors, we've added them. And do you remember the dot product formula? Here, I'll remind you that if I want to do A dotted, if I want to do A dotted with B, by definition, I know there's an easy way, right? Where we just multiply and add the numbers, but remember the definition is it's the magnitude of A times the magnitude of B times the cosine of the angle between them, right? This is the definition of the dot product. And see, here I almost have that, right? The only thing that's missing is the magnitude of A. So here's what I'm going to do. This is the way I like to think of it. If I take this and multiply in the magnitude of A right here, I'm not allowed to do that unless I also multiply the denominator by the magnitude of A. Because do you see, by doing this, I'm really just multiplying by 1, aren't I? Something divided by something is just 1. So I'm creatively adding this in here so that I can come up with the following formula. The component of B onto A can now be thought of as, by definition, the numerator is, you could either do B dotted with A or A dotted with B. I'm going to go A dotted with B, divided by the magnitude of A. And again, remember, this is the length of this vector here. It's the length of this. Length of my projection vector, or the magnitude of that. But here's why this is useful. Now, to find the projection vector, the projection of B onto A, remember that the characteristic feature of a vector should have magnitude and direction. Magnitude and direction. Magnitude, of course, is the same as length, right? So now that I know that this is giving me the length of my projection vector, I can think of this vector as the component of B onto A times, now what I need is a direction. What direction is the projection vector? I need to slide this back up here. Notice my projection vector is, what direction is it pointing in? It's pointing in the direction of A, isn't it? It's going in the same direction as A. But since I already have the length right here, what I want is a unit vector for A. That's just going to be A divided by the magnitude of A. Let me move that up here. This is a unit vector in the direction of A. So if I multiply, remember the unit vector has length 1, but I know it's going in the right direction. If I then multiply it by the correct length, then I get my projection vector. And this is the formula I choose to think of for my projection vector. Because what happens is, and this is what I saw in class, if you take this formula right here, put it right there, and it just looks overwhelming to me. It looks too messy. I lose all the meaning in what this formula is supposed to do. So I prefer to not put this here. You can if you want, but what I do is I think of these as two separate things. I know how to find my component, which is the length of my projection vector. And then once I have that, I'm just going to multiply that length times a unit vector in the direction of A. That's how I do it. Okay, and so let's do one example with this, and then we'll move on to matrices. This one's number 39 from 8.3. We'll work this all out here. And this was intriguing to me. Like I said, well, I may have told some of you, I'm not a bio major. I was an engineering major, so I get all the physics applications for vectors. They're really all over the place in physics and engineering. But I'm learning more about some of these applications in biology, which I find kind of cool and fascinating. So what they're describing here is researchers are trying to design a drug that alters the expression levels of 3 genes in a specific way. Okay, so and they're trying to get a desired change. They're trying to get these 3 genes to somehow, I don't know what these numbers mean, but it might be some kind of an expression, what you want each gene to do or something like that. And they want this to behave like 3, 9, -5. So gene 1, 2, 3 to have these characteristics, let's just say, right? One of the drugs that they're studying to try to get that desired change is this drug, which has an expression profile of B -2, 3, -5. And so the question essentially is how good is this vector at modeling this vector, right? How close is this expression profile to our desired expression profile? Well, for one thing, you can see it's spot on with the Z component, isn't it? It's exactly right here. Now you look at your middle one, that's not quite this, right? And here, whoa, we wanted a +3, we're getting a -2. So we want to find out how close this expression is to our desired expression profile. And so one way to think about that is if vector V right here, we've got the numbers there, looks like this, and vector B looks like this, one way to see how close B is to V is to think about how much of B, right? You could think of B as part of B is matching up with where you want it to be. You want it to be matching up with vector V. Of course, part of it is not, right? That's this part. But we want to have an idea of how much of B is basically going in the same direction as V. And that is exactly our projection vector. Now in the problem though, they say use a scalar projection. I thought we better talk about that. I know there's been some discussions in class, particularly on Monday, wrapping your head around the idea when something is a vector and when something is a scalar. Back to this, the component of A onto B, I'm saying is the length of the projection vector. Okay, so this is a scalar. That's just a number. When you do a dot product, you just get a number. And if you divide it by a magnitude, that's also a number. The projection vector itself is a vector. So when they say using scalar projections, they can't mean this because that is actually a vector. Scalar means they want this. They want the length of this vector. They want the component of B onto A. That's the length of the projection vector. That's what they mean by that. Okay. So now let's just do the computations and then we'll move on to matrices. So the component of B onto A is, or I guess we want B onto V. There we go. Change things up a little bit. That is going to be vector B dotted with vector V divided by, it's going in the same direction as vector V. The magnitude of vector V, I should say. let me write out these vectors because they're up here. So that would be 3, 9, -5 dotted with -2, 3, -5 divided by, remember, to find the magnitude of a vector, you're just going to divide, you're just going to do the square root of each part squared. I think I wrote these backwards, didn't I? This was V, this was B, but the order of the dot product doesn't matter. I actually did it backwards, but this is V, this is B, but that's okay. So the magnitude of V is the square root of 3 squared plus 9 squared plus -5 squared. And to do this dot product, we're just going to multiply and add. So 3 times -2 is -6, plus 9 times 3 is 27, plus -5 times -5 is +25, divided by, oh, help me out with this. 81, okay, this isn't bad. 81 plus 9 is 90 plus 25. I believe that's the square root of 115. And so this will give me -6 plus 27 is 21 plus 25 is 46 over the square root of 115. Is that what that is? 4.28? Thank you. Thank you. Okay. And now the final answer to the question, if you think about it, what they're basically saying is they want to know, like fraction wise, what fraction of the desired change is induced by drug B? Essentially what they want to know is, we now know this length. We want to know how much of V did we get? How much did we capture, right? So essentially we want to find the percent, this length divided by the total length. That will give us the fraction of the desired change. Fraction of desired change is essentially the what we just found, the component of B onto V divided by the length of V, which is the magnitude of V. So we ended up with, for this, 46 over the square root of 115. The magnitude of V is sitting right there. That is the square root of 115. So, you know, if you think of this as over 1, that's the same thing as 46 over root 115 times over 1 over root 15, root 115. That is 46 over 115, which has a decimal. Help me out here. Got a calculator. You must have a calculator out. I'm thinking about 0.4 something. .4? Is it around? Is it really about 0.4? Okay. 2 decimals, 0.40. It's exactly 0.4. Okay. Okay. So how could I interpret that? We could interpret that this vector B, which was drug B, has about, it captures about 40% of the desired change, right? Roughly 40% of the desired change. So anyhow, I thought that was kind of a cool application, and rather than just being asked, find the projection of this vector on this vector, of like, when would we ever use this, right? And so you can kind of use it to compare, you know, in this case, some desired, I don't know, was it exactly right? was this exactly, I was thinking it was just going to be like a weird random decimal, but if that came out to be exactly 0.4, then I guess I could say that's equal to 40%. Yeah, good point.